Hi students, in this video we will study how to design and implement full subtractor. Full subtractor is a combinational circuit that performs subtraction among 3 bits. That means, for example, suppose we have two numbers 1011 and 0110. Subtract 0110 from 1011. So for the first bit, the subtraction operation is 1 minus 0. So you can simply subtract 0 from 1 and the answer is 1. Difference is 1. Then for the second column, again it is a simple subtraction operation, that is 1 minus 1 is equal to 0. But for the third column, you have to subtract 1 from 0. So it is not possible to subtract 1 from 0. So you take a borrow from the fourth bit. Okay, when you take a borrow from the fourth bit, then the 0 becomes 10. So instead of 0, it is 10. So you can easily subtract 1 from 10 and you get the answer is 1. Okay, so while you taking the borrow from the fourth bit, actually you have to subtract 1 from this 1. Okay, when you subtract 1 from this one, this becomes 0. Okay, so for this fourth bit, actual operation is 1 minus 0. That means minuend is 1 and subtrahend is 1. That subtraction operation is performed. Then subtract the borrow bit. Okay, actually there is a borrow. Third column take a borrow from the fourth bit. So you have to subtract 1 from the minuend of the fourth column. Okay, so that subtraction, in that case it is borrow, and here it is the minuend bit and here it is the subtrahend bit. So 1 minus 1 is equal to 0. So here we get 0. Okay, so here we have to subtract 3 bit, that is minuend minus subtrahend minus borrow. Okay, in this case we make use of this full subtractor circuit. That means we have to subtract subtrahend from the minuend, but in that case, suppose there is a borrow occurs in that column for the preceding bit. Okay, so you have to subtract that borrow also from the result. After subtracting minuend, subtrahend from the minuend, you have to subtract borrow also. Okay, so there are 3 bits. So that is the case of the subtractor, full subtractor. That is the subtraction among 3 bits. Clear? So here we have to design a combinational circuit for performing the subtraction among 3 bits. So that is the statement of our problem. So next, identify the available inputs and the required outputs. So here we have to subtract 3 bits. So there are 3 inputs. Okay, inputs is equal to 3. Then you know that when you subtract 2 bits, you have a difference and a borrow. Same way, in the case of subtraction among 3 bits, you have a borrow and a difference. Okay, so there are 2 outputs. Next, you have to assign label for this input and outputs. So you can assign inputs as X, Y and Z. Then outputs are named as difference and borrow. Okay, then fourth step is build the truth table. So here there are 3 inputs and 2 outputs. So the truth table contains 5 columns. So here the 3 inputs are X, Y and Z. The outputs are difference and borrow. Okay, these 2 columns are the outputs and these 3 columns are the inputs, right? So there are 3 inputs. 2 raised to 3 is equal to 8 input combination, that is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. Okay, next we have to find the outputs. So 0 minus 0, 0, then 0 minus 0, 0. So difference is equal to 0 and borrow also equal to 0. Next is 0 minus 0 minus 1. So first you subtract 0 minus 0. 0 minus 0 is equal to 0. Then subtract 1 from 0. Okay, 0 minus 1 is equal to 1 with a borrow. Difference is equal to 1, borrow is equal to 1. Okay, next is 0 minus 1 minus 0. 0 minus 1 is equal to 1 with a borrow. Then subtract 0 from 1. That is 1 minus 0 is equal to 1. Then 1. So here it is, difference is equal to 1 and borrow is equal to 1. Next is 0 minus 1 minus 1. So first you subtract 0 minus 1. 0 minus 1 is equal to 1 with a borrow 1. Then subtract 1 from 1. 1 minus 1 is equal to 0. Then borrow 1. So here it is, difference is equal to 0 and borrow is equal to 1. Next is 1 minus 0 minus 0. 1 minus 0 is equal to 1. Then subtract 0 from 1. So again we have 1. So 1 with a borrow 0. Next is 1 minus 0 minus 1. Okay, 1 minus 0 is equal to 1. Then subtract 1 from 1. 1 minus 1 is equal to 0. 0 with a borrow 0. Next is 1 minus 1 minus 0. So 1 minus 1 is equal to 0. Then 0 minus 0 is equal to 0. 0 with a borrow 0. Next is 1 minus 1 minus 1. 1 minus 1 is equal to 0. Then 0 minus 1 is equal to 1 with a borrow. So here difference is equal to 1 and borrow is equal to 1. Okay. So this is the truth table for the full subtractor. Okay. So fifth step is find the minimized Boolean expression for both D and B. For this we draw the K-map and find the expression. So here this is the K-map for the difference and this one is for the borrow. Okay, so here we have the variables x, y, z. Then yz may be 0, 0, 0, 1, 1, 1, 1, 0. And here also 0, 0, 0, 1, 1, 1, 1, 0. X may be 0 or 1. So in the case of difference is equal to 1 in the case of 0, 0, 1, 0, 1, 0, 1, 0, 0 and 1, 1, 1. And borrow is equal to 1, 4, 0, 0, 1, 0, 1, 0, 0, 1, 1 and 1, 1, 1. So in the case of difference, we cannot group the ones. So we can write the expression as, so for this one it is x bar, y bar, z plus. This one it is x bar, y, z bar plus. For this one it is x, y bar, z bar plus. This one x, y, z. Okay. So apply distributive law for the first and second term. So we have x bar into y bar z plus y z bar plus, again apply distributive law for this term, that is x into y bar z bar plus y z. Okay, so this is equal to x bar into y bar z plus y z bar is equal to y XOR z plus x into y bar z bar plus y z is equal to y XOR z. Okay, so this is equal to x bar into y XOR z plus x into XOR z. Y XOR z can be written as y XOR z complement. Okay, so see this here, this one is y XOR z and here it is y XOR z whole bar, that is x bar. Suppose take this as y, x bar y plus x y bar, that is x XOR y, that is x XOR y XOR z. So this is the expression for the difference, right? Next we can find the simplified Boolean expression for borrow. So for this we group the ones in the K-map. So here we can group a pair, then second pair, then third pair. Okay, so the expression is b is equal to, for the first pair it is x bar, y is cancelled, z, plus for the second pair it is x bar, z is cancelled, y, plus for the third pair x is cancelled, then yz. So this is a simplified Boolean expression for the borrow. But when you implement this expression, you should have a NOT gate, AND gate and OR gate. Okay. First you should complement x bar, then one AND gate for this term and one for this term and one for this term, then OR the terms. So this is an additional gates required for the implementation of this borrow. So to avoid that problem, we have to find the borrow expression in terms of XOR gate. Okay, so we write all the minterms as such without any grouping. That is, we write the borrow expression as b is equal to, the expression for this one is x bar, y bar, z plus, this one is x bar, yz plus, this one is x bar, yz bar plus, this one is xyz. Okay, so that is equal to, apply distributive law for the first and last term, that is z into x bar, y bar plus xy, plus then second and the third term again apply distributive law, that is x bar y into z plus z bar. Okay, so z plus z bar is equal to 1, so here it is x bar y, then z into x bar y plus xy is equal to x nor y, plus here it is x bar y. Okay, so this is equal to z into x nor y is equal to x or y complement plus x bar y. Okay, so this is the Boolean expression for the borrow. So here we have an XOR gate and complement it, then AND gate and OR gate is required for that. Okay, so it is easy to implement the logic circuit for this borrow. Clear? Then sixth step is implementation. So we can implement this full subtractor using basic gates and XOR gate and also universal gates. Okay, so we saw that the difference equation is equal to x XOR y XOR z, and borrow is equal to z into x XOR y whole bar plus x bar y. Okay, so first we can implement the circuit using basic gates and XOR gate. So here we have an XOR gate with two inputs x and y. So here we have x XOR y. Then take the third input z and x XOR y, both are given to another XOR gate. So here we have the output x XOR y XOR z. So that is the difference. Okay, then borrow is equal to z into x XOR y whole bar. So here we take the x XOR y. Okay, complement it using NOT gate. Okay, so here we have x XOR y complement. Then take z, both are ANDed together. Here we get z into x XOR y whole bar. Then take x, complement it using NOT gate. So we have x bar. Then take y, both are ANDed together. Here we have the output x bar y. Then this x bar y and z into x XOR y bar, both are OR together. We get z into x XOR y bar plus x bar y. So this is the borrow, right? So this is the implementation of full subtractor using XOR gate and basic gates. Okay. Next is implementation of full subtractor using NAND logic. Okay. So we know that difference is equal to X XOR Y XOR Z. Okay. So we know X XOR Y. How can we implement X XOR Y using NAND logic? See the video, implementation of all other gates using NAND gate for the derivation of the expression X XOR Y using NAND gate. So in that video we derive it as X into XY bar into Y into XY bar whole bar, here also whole bar. Okay, so take it as P, then we can write this X XOR Y as P XOR Z. So P XOR Z can be written as P into PZ bar whole bar dot Z into PZ bar whole bar. Right? So we have the expression B is equal to Z into X XOR Y bar plus X bar Y. Okay. So we know that X XOR Y is equal to P. So this can be written as ZP bar plus X bar Y. Right. Then we rewrite this expression as ZP bar plus ZZ bar plus X bar Y plus YY bar. So here ZZ bar is equal to 0. So ZP bar plus 0 is equal to ZP bar itself. Here also YY bar is equal to 0. So X bar Y plus 0 is equal to X bar Y itself. Right. Then apply distributive law, that is Z into P bar plus Z bar plus here it is Y into X bar plus Y bar. Right. So we can write it as Z into, here apply De Morgan's, so PZ bar plus Y into XY bar. Here also apply De Morgan's law. Right. Next we can write it as Z into PZ bar plus Y into XY bar double bar. Okay. Then apply De Morgan's, that is Z into PZ bar whole bar dot Y into XY bar whole bar. Okay. Clear. So this is the expression for the board. Now we can implement this using NAND logic. Right. Next we can implement this full subtractor using NAND gate. So here we have a NAND gate with two inputs X and Y. So here we have the output XY bar. Then take this X input NANDed with XY bar. So we get X into XY bar whole bar. Similarly take this XY bar and NANDed with Y. Here we have Y into XY bar whole bar. Then these two outputs are again given to another NAND gate. So here we get the output as X into XY bar whole bar dot Y into XY bar whole bar. Okay, that is actually P. Okay, then take Z input. Okay, Z and P are NANDed together, we have PZ bar. Then take this P and PZ bar, both are NANDed together, we have P into PZ bar whole bar. Similarly PZ bar is NANDed with Z, we get Z into PZ bar whole bar. Then these two outputs are again NANDed together, we get the difference, that is equal to P into PZ bar whole bar dot Z into pz bar whole bar whole bar. Okay, so this is the difference. Here we have the difference. Then next we can implement borrow. So in the case of borrow, first is z into pz bar whole bar. So here we have z into pz bar whole bar, this one. Then y into xy bar whole bar. So here we have y into xy bar whole bar. Take this output. It is NANDed with this one. So here we have the borrow, that is equal to y into xy bar whole bar dot z into pz bar whole bar whole bar. Okay, so this is the borrow. Okay, this is how we can implement full subtractor using NAND logic. Okay, next is implementation of full subtractor using NOR gate. Okay, so we know that difference is equal to x XOR y XOR z. Okay, so we can take p is equal to x XOR y. So x XOR y, we know how to implement XOR gate using NOR gate. See the video implementation of all other gates using NOR gate for the derivation. So in that video we derived x XOR y as x plus y bar whole bar plus y plus x plus y bar whole bar whole bar. Okay, now we can write d as p XOR z. Okay, so we can write it as p plus z bar whole bar plus z plus p plus z bar whole bar whole bar. Okay, so this is the Boolean expression for difference using NOR gate. Clear? Then we have the borrow. Borrow is equal to z into x XOR y whole bar plus x bar y. Clear? So we know x XOR y is equal to p, so we can write it as set p bar plus x bar y. Rewrite it as set p bar plus p bar plus x bar y plus x bar. So p bar is equal to 0, so set p bar plus 0 is equal to set p bar itself. X bar is equal to 0, so x bar y plus 0 is equal to x bar y itself. Okay, so apply distributive law. So here it is p bar into set plus p plus, here also apply distributive law, so x bar into x plus y, right? So this can be written as p bar into set plus p plus x bar into x plus y double bar, whole double bar, right? Then apply De Morgan's law, that is p bar into set plus p whole bar dot x bar into x plus y whole bar whole bar. Okay, then again apply De Morgan's here, that is p double bar plus set plus p bar dot x double bar plus x plus y bar then whole bar, that is equal to p double bar is equal to p. Again we apply De Morgan, so p plus set plus p bar whole bar plus x double bar is x plus y bar whole bar. Okay, so this is the expression for the borrow. Okay, so we get the expression of difference and borrow in terms of NOR logic. Now we can draw the logic circuit, right? Next we can draw the logic circuit of full subtractor using NOR gate. So here we have a NOR gate with two inputs x and y, and here we get x plus y bar. Then take x input, then node with x plus y bar. Okay, so here we get x plus y bar whole bar. Okay, similarly x plus y bar is node with y. Here we have y plus x plus y bar whole bar. Okay, then we take these two outputs and node together. Then we get x plus y bar whole bar plus y plus x plus y bar whole bar. It is actually p. Next, take this p input and z input, node together. Okay, this one is z. So here we have p plus z bar. Then take this p input, then p plus z bar, node together. Okay, so here we have p plus z bar whole bar. Similarly we take p plus z bar and z, both are node together. Okay, so that is z plus p plus z bar whole bar. Then these two outputs are again node together. So we get the difference. Difference is equal to p plus z bar whole bar plus z plus p plus z bar whole bar. That is the difference. Next we have to find the borrow. So borrow is equal to p plus z bar whole bar. So here we have p plus z bar whole bar. So this one. So this one is the p plus z bar whole bar. The next is x plus y bar whole bar. So here we have x plus y bar whole bar. Okay, take these two outputs, node together. Okay, so we get x plus y bar whole bar plus p plus z bar whole bar. Okay, so next we have to complement it. Okay, so here we get the borrow. Okay, that is x plus y bar whole bar plus p plus z bar whole bar double bar, right? So this is the borrow. Clear? So this is the implementation of difference and borrow of the full subtractor using NOR logic. Clear? So this is how we can design full subtractor using basic gates and XOR gate, and also NOR logic and NAND logic. Okay, thank you.